Well, how did you do with this question that I asked at the end of the last part of the video? We know that the ball started from rest, and a stationary object by definition has no kinetic energy, so the initial kinetic energy has to be 0. Also, we know that the ball has gone down, and things have more gravitational potential energy when they're higher up, and so the gravitational potential energy must have decreased. In C, we're showing it having increased, which it can't have done. So the answer is D.
Still staying with this example just a little while longer, let's notice one more thing about it. So if we think about the time when y3 is the same as y1, in other words, when the ball has returned to its original height, then since y1 and y3 are the same, that tells us that the gravitational potential energies at times 1 and 3 are the same. And since the total energy is a constant, that tells you that the kinetic energies at time 1 and time 3 must also be equal. But notice the velocities, v3 and v1, are not the same because they're in opposite directions. But this is telling you that while those velocities are in the opposite directions, the speeds are the same, because the kinetic energy doesn't care about the direction of the velocity. It only cares about speed. Energy is a scalar. And so the kinetic energy, when I write it this way, note there's no vector symbol on that v, and I haven't put anything in bold. This is a scalar expression. That v there is a speed, not a velocity. Similarly, when you look at the gravitational potential energy, that y is not a position, which would be a vector. It's the vertical component of the position. And while vectors are made out of components, components themselves are scalars. Let's see how energy being a scalar can save you a lot of work. So quite some time ago, we were doing projectile motion. And so here's a typical sort of projectile situation to think about. I throw this ball. I'm at the top of a cliff or something. The ball is initially 8 meters above the ground. I throw it at 10 meters per second, angled 60 degrees above the horizontal. And let's say we want to know its speed, not velocity, its speed just before hitting the ground. Well, you could work through this with projectile motion methods that we've learned, but it would take you a little while because you'd have to worry about the x component of v, which is constant, and then a y component, and so on. And the y component is varying. But if we use energy, we can sort of cut through a lot of that detail. We know it starts with some amount of kinetic energy. We also know that before it hits the ground, it's lower down. It should be going faster. And I've set my axes up here, so my initial value of y is 0. So I can say that the gravitational potential energy at time 1 is 0. The gravitational potential energy at time 2, well, that's at a negative y, so that's going to come out negative. There's nothing wrong with a potential energy being negative. It's a scalar, but it can be positive or negative. And so we can now just go ahead and write our conservation of energy. K1 equals K2 plus UG2. And now let's solve for V2 out of here. So I'm going to go ahead and rewrite this as a half m V1 squared equals a half m V2 squared plus mgy2, although I'll note that y2 is a negative number. And like before, the masses are going to cancel. And I come up with 16.1 meters per second. Notice that because energy is a scalar, I could just ignore the 60 degrees. All I care about is the speed, There is the initial speed, and so I was able to just use it and solve straight for the speed just before the ball hits the ground. Now, on the other hand, if I wanted to know what angle it was going at just before it hit the ground, I'd have some more work to do, and energy wouldn't be very good at that. This is the trade-off. Energy is insensitive to direction, so if you don't care about energy, about direction, energy will save you a lot of work. But if you do need to know information about directions, energy is not a good way to get it.
In the problem I just worked, I defined my axes so that the origin was at the initial location of the ball. But what if I had decided differently? What if I had located the origin down on the ground, which might be what you're more inclined to do? In that case, what would the energy bar chart look like?